Welcome to this video. We are going to solve some trigonometric equations, specifically quadratic structure, where you're looking at a sine squared or a cosine squared theta. But we are going to add in the trick where we have to substitute it out using the Pythagorean identities. So we will also talk about the Pythagorean identities, which is a very, very important and useful and frequently appearing type of identity that you'll use in trigonometric classes and above. So we're going to go ahead and solve some trig equations. You'll need your sine and cosine values of a unit circle. You'll need to know how to solve quadratic equations, either by factoring or using the square root property. And the big one for this lesson, making substitutions using the Pythagorean identities. So what the heck are the Pythagorean identities? The Pythagorean identities are trigonometric identities derived from applying the Pythagorean theorem to the unit circle. In the unit circle, the radius is 1, and the legs of the corresponding right triangle are cosine of theta, that's your x, and your sine theta is your y. So if I go ahead and I look at a right triangle, here's my right triangle, the Pythagorean theorem says a squared plus b squared, those are my two legs, squared will equal c squared. So in this case, my a, that can be x squared, plus my y squared is going to equal my radius squared. Well, my radius is 1 squared. So I can go ahead and substitute out x, and we get cosine squared theta plus sine squared theta is going to equal 1. And this is the Pythagorean identity. And you usually see it sine squared plus cosine squared theta equals 1. But that is the main, most important Pythagorean identity. All of the other trigonometric formulas can be derived from this one function using basic algebraic principles, okay? So there are others, right? Because say I didn't want it to be equal to 1. Say I wanted to just go ahead and substitute out sine squared. Well, I could subtract cosine squared, right, from either side. So this is another form of the identity. Or let's say I want cosine squared isolated. Well, I could subtract sine squared on both sides. So just notice kind of some pattern here. Sine squared theta equals 1 minus cosine. Cosine squared is 1 minus sine squared. These are the main three that we're going to be using in this lesson, and mainly these second ones. But we could go ahead and manipulate this further by dividing by sine and cosine, right? That would incorporate our other functions. 1, if we divide by sine squared, we get sine over sine, that gives us 1. Plus cosine over sine gives us cotangent squared theta is equal to 1 over sine squared theta, which is cosecant. So here's another form, and then the same idea, if we divide by cosine squared theta, we would get tan squared theta plus 1 is equal to secant squared theta. Okay, so anyway, here's a lovely chart that details all of the Pythagorean identities, right? This is your main one. These can appear. I don't ask you or advocate that you store these in your memory banks. If you have the brain width to go ahead and do this, then do that. But what I recommend is memorizing your first one and knowing how to get to all of these other ones. That's what's important. So we're going to look at some trigonometric equations today with quadratic structure, but the catch is going to be that one of the trig functions is going to be different than another trig function. So here's what we do. First, make sure your equation's in standard form. If the equation involves two different trig functions, one squared and one not, use the Pythagorean identity to rewrite the squared function in terms of the other function. Okay, then you'll use a quadratic strategy. Usually with these problems, it's factoring. You'll have to go ahead and combine some like terms, factor it, and then solve. Number 3, find the angle measures by using your unit circle. So let's look at an example. What the heck would this look like? The function h is given by h of x equals 2 cosine squared minus 3 sine x minus 3. Find all the values of x for 0 to 2 pi, excluding 2 pi, for which h of x is equal to 0. Okay, so my function is 2 cosine squared x minus 3 sine x minus 3. And we want that to be equal to 0. Now, here's the catch. Here's the rub. Notice my two trig functions are separate. Okay, that puts me in some hot water. So what I want is I want this cosine squared theta, I want that to be subbed out. And so you right there should know, hey, I have to use my Pythagorean identity. And so if you don't know, which one you're going to use off the bat, write down the general Pythagorean identity, right? And an easy way to remember this is I've seen wedding rings. This is probably for nerds, but wedding rings where one says sine squared and then the other person says cosine squared. Oh, and together they make one. Right? Isn't that sweet, right? That's some math riz for you. So if you don't know, okay, what's cosine squared? Well, generate this, and then how do you isolate cosine squared? So here's the identity we're going to use. Cosine squared x equals 1 minus sine squared x. And I'm just going to substitute that. So I have 2 times 1 minus sine squared x minus 3 sine x minus 3 equals 0. And we're going to go ahead and distribute this 2. We're going to distribute the 2. So I get 2 minus 2 sine squared x minus 3 sine x minus 3 equals 0. Now, you're going to have to go ahead and combine some like terms. And two, what I like to do is I don't know. Let's combine some like terms. And then I'll figure out what I want to do. 2 combined with the negative 3 gives me a negative 1. So I get negative 2 sine squared x minus 3 sine x minus 1 equals 0. Now I want to factor this. I don't like the negative in the front. So you know what I'm going to do? I'm going to change the signs of everything. I'm going to multiply this side by negative 1. And I'll multiply this side by negative 1. And you know what happens on the right-hand side? Nothing. And that's what's kind of great. The other way of looking at this is I could change everything over to this side. But I really want my leading term, that 2 sine squared x, to be positive. Plus 3 sine x plus 1 equals 0. Now, this is a function I can work with, right? And this might scare some people, but remember, if this freaks you out, what if it was a polynomial? What if it was 2x squared plus 3x plus 1? And hopefully that's a little less scarier. You just want to factor that, right? So I'm going to split my first term, 2 sine x, and then I have 1. It has to be a 1 and a 1. And everything's positive. This is actually really easy factorization. There's not many options. Okay? So 2 sine x plus another sine x gives us 3 sine x. We're good. Equals 0. So 2 possible solutions here when we're going to go ahead and solve. 2 sine x plus 1 equals 0. And sine x plus 1 equals 0. So I'm going to solve these. I'll subtract 1 on each side. We get 2 sine x equals negative 1, right? I just subtract 1. Then we'll go ahead and divide by 2. And so I get sine x equals negative 1/2. I want my y value to equal negative 1/2. This is going to be a pi 6 angle, but it's negative. So that's going to be in the southern hemisphere. So 7 pi 6 and 11 pi 6. And then over here, I can go ahead and subtract 1. And we get sine of x equals negative 1. Well, that only happens at the South Pole. So we get 3 pi halves here, okay? So let's see, do we keep all these? What do they want? All values at x on 0 to 2 pi. Yep, so these are the winners. There you go. That is how you use the Pythagorean identity to go ahead and solve, okay? All right, example number 2, before I go ahead and give you some practice ones. Here they say the function d is given by d of x equals 2 sine squared x plus root 3 cosine x. Ah, shucks. Different trig functions again. So we're going to have to make a substitution with the Pythagorean identity. Find all values of x for 0 to 2 pi where d of x equals 2. Okay, let's go ahead and take 2 sine squared x plus root 3 cosine x and set that equal to 2. And again, what we're going to do over here is we're going to take our Pythagorean identity. A squared plus b squared equals c squared. I want sine squared isolated, so I'm subtracting cosine on both sides. 1 minus cosine squared x. See, you don't have to store all those crazy formulas. You just start with one and you get to the other one. So I'm going to substitute this out. All right, so we end up getting 2 times 1 minus cosine squared x. I substitute that out. and we'll have to distribute. So 2 minus 2 cosine squared x plus root 3 cosine x equals 2. Okay, what do we want to do? Let's combine our like terms. I got a 2 over here and a 2 over here, so let's subtract 2 on each side. Okay, I have negative 2 cosine squared x plus root 3 cosine x equals 0. And what I'm going to do, I could change my signs. Sure, why don't I just do that? Just because that bugs me. Minus root 3 cosine x. So I'm changing the signs of everything, right? Dividing by a negative 1, or I'm moving everything over to the other side, however you want to look at it. And then notice, I don't have a trinomial. I don't have a constant term here. So when you don't have a constant term, your factoring is going to be GCF, a greatest common factor. And what they have in common is a cosine. So I'm going to go ahead, I'm going to factor out a cosine of x, and that leaves behind 2 cosine of x minus a square root of 3 is equal to 0. So 2 possible solutions, cosine of x equals 0, and that's going to happen at 2 locations, North Pole and South Pole in the unit circle. And then we have this other equation, 2 cosine x minus the square root of 3 equals 0. We could solve this. Add square root of 3. Then we'll divide by 2. Divide by the 2. Okay. And so where does our x value equal square root of 3 over 2? That's going to be the pi third angles, pi 3, and I want the other positive one, that's what, 5 pi over 3, quadrant 4. Okay, so 2 solutions there, or actually 4 solutions, sorry. Pi halves, 3 pi halves, pi thirds, 5 pi thirds. Okay, all right. That's pretty much it. This is similar to the last lesson. The only thing is we just have to work in our Pythagorean identity. Please pause me. I want you to try this example, and then I'll show you the solution. Okay, hopefully this is what you got for this problem. I have 4 solutions, 0, pi, pi 6, and 5 pi over 6. How we did it, we went ahead and substituted out cosine squared of x for 1 minus sine squared, and then we went ahead and distributed that 2 to both terms. Now 2 minus 2, those cancel out, and so we get negative 2 sine squared x plus sine of x is equal to 0. I went ahead and I just multiplied both sides by a negative 1 or divided by a negative 1. I changed the signs of everything. So this is positive and this is now negative. And then I went ahead and did a GCF, greatest common factor of sine of x. I took that out. I used the zero product property, set them both equal to 0 to solve, and our first solution yielded 0 and pi. In our second solution, we added 1 and then divided by 2. Right here, divide by 2, you get sine of x equals 1/2. Well, that's pi 6, and that is 5 pi over 6. So hopefully you got that. Awesome. Last example or last practice here for this lesson. Go ahead, please pause me. I want you to try this, and I'll talk through the solution. All right. For this example, 3 solutions, pi thirds, 5 pi thirds, and pi. How did we get there? We set the equation g equal to 1, and then we went ahead, since our trig functions were different functions, we have to swap out this sine squared x for 1 minus cosine squared x. Again, we distribute, right, yielding 2 minus 2 cosine squared x minus cosine x. I went ahead and subtracted 1 on both sides in order to move that term over, and that's how we end up with the plus 1 here. And again, I don't like my leading term being negative, so I change the signs on everything. I make this a positive, this is now a positive, and this is now a negative. And then this is a trinomial, so we have to factor that into 2 binomials. You get 2 cosine x minus 1, cosine x plus 1 equals 0, and you solve each factor equal to 0. Add 1 here to both sides, divide by 2. We've kind of seen that story multiple times now, and we get pi thirds, 5 pi thirds. Cosine x plus 1 equals 0. Well, that means cosine of x is equal to negative 1 after we subtract 1, and you get negative 1 at angle pi. Okay, hopefully in this video you learned how to utilize the Pythagorean identities, mainly these ones here, in order to substitute them out and put a quadratic equation in terms of the same trig function. You cannot solve if they're in different trig functions. So that's what we learned. Anyway, we're solving a quadratic trig functions. Give this video a thumbs up if you learned something. I'll see you in the next lesson. Take care.